Welcome back to Chapter 2. Last section we were learning a bit about lines and quadratics. Today we're going to be expanding that into modeling with power functions. So the first question you're probably wondering is, okay, what is a power function? Well, we'll get there. That'll be the first thing we talk about. After, of course, learning targets. So we're going to identify and analyze power functions, write statements as power functions, write power functions as statements, graph power functions, and model data with power functions. So as soon as you know what power functions are, that will help clarify things just a little bit. So, what are power functions? Power functions are they can be written in the form y equals a number times x to a power. That's all it is. So, we have some number, it's k times x to the a. K is called the constant of variation. A is called the power. A does not need to be an integer. It does not need to be positive. We could have y equals 3 times x to the negative 7/5 if we wanted to. That would be a power function. These are either direct or inverse variation functions, as we'll see in a minute when we get some examples. And it's also a proportional thing. So if we had like y equals x squared, y is directly proportional to the square of x, or y is directly proportional to x squared. Y varies directly as x squared. So I know that we see these kind of direct and inverse variation problems in both algebra and algebra 2. This is just taking it another step. So some examples of some power functions. We have circumference of a circle. C equals 2 pi r. The power is 1. The constant of variation is 2 pi. We would say that the circumference varies directly as the radius of the circle. The area of the circle, a equals pi r squared. The power is 2. Constant variation is pi. So the area of a circle varies directly as the square of its radius. The force of gravity. The force equals k divided by the distance away from the center squared. So the power is -2 because we could rewrite this as k times d to the -2. Notice that's what the power function is written as. It's not over x to the something, it's times x to the something. So that exponent may have to be negative. So the power there is -2, the constant variation is k. So here, the force of gravity varies inversely because it's a negative power, so it varies inversely as opposed to directly with a positive power. The force of gravity varies inversely to the square of the distance away from the center. And Boyle's law, the volume of a gas at a constant temperature is inversely proportional to the pressure of the gas. So again, this could be written as V equals K times P to the -1. So the power is -1. The constant variation is K, which is actually, it's a constant, Boyle's constant. And so that's what some of these power functions are. Now, when we are analyzing the power functions, it'll tell us to find the power and the constant variation, which we just talked about that a little bit, and then graph and analyze. Like when you're graphing these, probably use a graphing utility, either a graphing calculator or Desmos. One of those would be great. And then when you analyze, things you need to talk about: the domain and the range. You always want to talk about the domain and the range of the function. Where are they possible or where are they not possible? All right, and we've talked about domain and range a lot, but just the domain, what could x be? Range, what could y be? Is it continuous or are there discontinuities? That would be breaks in the graph. So are there any holes or breaks? A lot of times we'll get breaks with asymptotes. So that would be something to talk about. Now, what's nice about the assignments is that it would take you through anything that it wanted you to talk about. You don't have to remember to talk about all these things, and you probably won't talk about every single thing for every single problem. Where is it increasing or decreasing? So if we had, say, the graph of y equals 1 over x squared, which would be y equals x to the negative 2, that graph looks kind of like this. So it's increasing when x is less than 0 because the graph is going up. So it would be from, say, negative infinity to 0, but not actually at 0 because there'd be a discontinuity there. The range of this, by the way, y is greater than 0, and the domain x can't equal 0. And so it's increasing from negative infinity to 0. It's decreasing, it's going down from 0 to positive infinity. Any kind of symmetry. This is symmetric across the y-axis. So that's something that we could notice. It could also have be symmetric about the origin, which would be the 180-degree rotational symmetry that we get with odd functions, where if you have it graphed and you flip your graph upside down, it looks the same. We could have vertical symmetry. We could have symmetry across the line y equals x. Probably not in these cases, but I mean that is a type of symmetry that comes up from time to time. No, never mind. Those wouldn't be functions. Is it bounded above or below? In this case, it's bounded below, and we know that because the range has to be greater than 0. So it's bounded. It doesn't continue. Where if we had something like y equals x cubed, looks kind of like that, that's unbounded from either above or below. Local extrema. That would be any kind of maximums or minimums that we can see. Neither of these have any. If we had something like a quadratic, this would have a local maximum right there. We could actually find that value if we wanted to. Asymptotes, where does it have asymptotes? Those could be vertical asymptotes. Those could be horizontal asymptotes as well. But asymptotes are generally thinking vertical, but they could be either. The only one we have asymptotes on is this one here, and the asymptote would be at x equals 0. The end behavior, what's it doing when x is going to infinity or negative infinity? So for our 1 over x squared, it's going to 0 when it's going either way. When it's going to negative infinity, it's getting closer to 0. When it's going to positive infinity, it's getting closer to 0. The x cubed, it's getting closer to negative infinity when x is going to negative infinity, and positive infinity when x is going to positive infinity. And the quadratic here, it's going to negative infinity both ways. So when x is going to negative infinity, y is going to go to negative infinity, and also the other way. Graphs of power functions. We can graph these. They do have some consistencies that we can look at. So if we're looking in the first or fourth quadrants, all the power functions will always look like this. So the top graph is when k is greater than 0. And the bottom graph is when k is less than 0, because that would give us that vertical reflection. And then we can see what our exponents are. If the exponent equals 1, it's just linear. When the exponent is less than 1, but bigger than 0, we get that downward curve. That's where we have like square root functions and stuff like that, because a square root is just a 1/2 exponent. When x is bigger than 1, we get the upward curve, like y equals x squared. It curves upwards. When the exponent is negative, we get this other curve that has an asymptote at both axes, because we'd have y equals 1 over x to a power. So x can't equal 0 because the asymptote, and then y won't equal 0 because you can't get 0 by dividing by something. So neither will equal 0, so you have asymptotes on both ways. The same thing, when k is less than 0, you get this other stuff. It's just been reflected. Now, what is the other part of the graph going to look like? Well, there's going to be 3 different options, 3 different things that could happen here. So one thing is that there will be no other part of the graph. It's undefined when x is less than 0. Things like y equals the square root of x is undefined for x is less than 0. So that's a possibility. It could be an even function, in which case it would be symmetric. So we would just like flip it across the y-axis and we'd get the same thing. So it would either be going up again or it would be going down again. It would be going the same direction. Or it's an odd function, in which case it would be symmetric about the origin, where we would, instead of flipping it across the y-axis, we would turn it upside down, and that would be that other part of the graph. So for instance, it would go, like if we're looking at this red one in the top, it would go like that. Or the blue one there would go like that. So those would be the odd functions. So those are the only things those graphs can do. Monomial functions. A monomial function is, it looks like a power function, but the specific there is n is a positive integer. The exponent has to be a positive integer. So we don't have the negatives, we don't have the decimals or anything like that. When we're looking at monomial functions, there are 2 different shapes. We have our even functions, which look kind of like quadratics, where they're going to be going like that. And we have the odd functions, which look like cubics, which go like that. Now, a linear function, x to the first, that's an odd function. It looks kind of like a cubic. It's just flattened out. The higher the exponent gets, the steeper it gets. So if we wanted, say, y to the 4th, it would be even, and it would just be steeper. If we wanted x to the 5th, it would be odd, and it would be steeper. So we can see like they'll always have those shapes. And then what would we do to graph these? We would look at the vertical stretch and vertical reflection. That's really all that we're going to be doing to graph these, because this value of k here is a vertical stretch and possibly a reflection if it's negative. So if the value is bigger than 1, it'll be stretched kind of like we did for these blue graphs. If the value is less than 1 but positive, it would be flatter. If the value is negative, you're going to have that vertical reflection. We've seen all that stuff quite a bit. And then modeling with power functions. So modeling with power functions is when we do that regression line. We've done regression for linear and quadratic. For power, it's going to be basically the same. In the calculator, you're going to have to enter your data, and then you choose the power regression. It would be this A down here. But the data gets entered the same into list 1 and list 2, and everything's the same. And what it does is it gives you the y equals a times x to the b. and then A equals something, B equals something. Chances are B will equal something fairly horrible. Um, I would look to see what it's close to. A lot of times you'll get like y equals 3 times x to the 0.49987. Well, 0.49987 is basically a 0.5. X to the 1/2 is a square root graph, so that would probably be a square root. So I wouldn't go with the full decimals. Now, if you got like 1.3, yeah, maybe you just leave that as 1.3. But a lot of times it's going to be really close to something we know. Like if you get like 2.974, that's probably a cubic. I'd go x to the third. So doing it in the calculator, it's the same, except you use the power regression. Doing it on Desmos. I love the regression features on Desmos. It is fantastic. So first, I would type in the regression equation. Now, I did not type it in to look like that. I typed y1, just like the normal one. It puts it down in that subscript by itself. The tilde, which is the number, it's like the second or the shift, the number key. Except it wouldn't be a number, it would be the one that's just to the left of the 1 on the keyboard. And then k x1, and then the caret to get the exponent to the a. And it puts it into that form. And then the next one, you just need to put a table. To enter a table, you click this little plus sign and choose Add a Table. Table gets added in. I know when mine got added in, these were x2 and y2, so I just went and I changed it to x1 and y1. Now you can put your points, put your values right in the table. It'll come up in the graph, which is over here, and your equation will form. It'll pop down, it'll start forming the equation, give you your correlation, which doesn't mean as much being that it's not linear, but it's still being used as a how close to a match is it. Um, so uh, it's really quite slick how that one works out. Um, yeah, so anyway, so this is modeling with power functions. Um, I will see you in class where we will be doing a little bit of modeling and matching. But until then, keep working problems, keep asking questions, and as always, happy mathing.